My name is Maha Kalaji. I'm from the Asteroid Foundation. Can I ask you first to be kind enough to turn your telephones to silent? This session is being recorded and streamed online. So please turn your telephones off, or at least on silence. So welcome to the Asteroid Day Space Lecture for 2024. And there are people who are joining us online. I would like to welcome you to this live broadcast from Luxembourg. You have a chance to ask questions afterwards. We'll try and address them today. If not, somebody will respond to you at a later date. We have a very interesting program today. And before we start that program, I would like to thank the people who actually made this event possible. Quite a few of you here are due to the generous support from the Luxembourg Space Agency. Without them, we wouldn't be able to run this program. The Luxembourg Fonds National de Recherche, the André Loche Foundation, the Luxembourg House of Financial Technology, Sofitel, where quite a few are staying, and Ville de Luxembourg, who gave us this wonderful building for today and tomorrow. The Chamber of Commerce, Perpetuity Capital Fund from Australia, GLAY, Redwire, GomSpace, and we'll have a talk from somebody representing GomSpace, OHB, Offworld, and the Embassy of Switzerland in Luxembourg. The session is divided, or this program is divided into 3 sessions. Initially, first of all, we'll have 4 talks. Can I ask the speakers to stick to 10 minutes, please? 10 to 12 minutes, give some time for questions. And then we'll have a short break where you can have some water or whatever. We'll come back to the keynote afterwards by GomSpace. And then I'll hand over the microphone for the panel where Patrick Michel is somewhere here. Patrick Michel is there. He will take over the last part of it. We will finish at roughly 8:15. After that, we have the event in the Museum of Natural History, where will be Gianluca Massi, who is here also, will control a telescope virtually from here in Tuscany to show us an asteroid which is getting close by, but not close enough, as Julie told me today. Okay, without further ado, I'd like to welcome the first speaker, who is Mirel Birlan from CNRS in Paris. He did his postgraduate studies in Romania. Then he joined CNRS Paris 7, yes, at the Paris Observatory and stayed there until 2021, when he became the director of the Astronomical Institute of the Romanian Academy of Sciences, and he still holds that position until today. He specializes in astronomical observations of solar system bodies, mainly asteroids, and he had written about 150 scientific articles in astronomy and planetary science. But he also had written 3 children books. And so I'm not sure if you're going to be talking about that today, but today he'll be talking about the colors, shapes, and composition of asteroids. Please welcome Mirel Birlan.
Bonjour à tous. Hello, everybody. As my colleague said, I am Romanian, native Romanian. I moved during this life also in Europe, in the United States, move around the places that we put telescopes, because we astronomers are a little bit scared about the light, and also the light pollution, and also the clouds and so on. So we like to stay outside the city, and also outside the places where there are crowded of people, and also we are a little bit savage. So I will start talking about my job, but can I have the? Oh, perfect. But I will start by making a little bit of advertising about Romania and also the Astronomical Institute where I am now. I must say that I am now in the CNRS, and CNRS is a wonderful company. It's a wonderful place on which, when we want to achieve another experience, they say, okay, and move. And after a while, come back and say if you are happy or not. We will. You can join us after 1 year, 2 years, 3 years, 4 years, up to 6 years. So I have a mandate now for 4 years. This is my last year. So maybe I will move back to Paris, to Paris Observatory after this year. So I am now in the Astronomical Institute of Romanian Academy. So what does it mean, Romanian Institute? It means, let's say, 3 sites in Bucharest, in Cluj-Napoca, in Timișoara. Maybe you are aware about Romania. Maybe you have already visited. And also, during the last 5 years, we installed a new facility, a new assets in Transylvania, modern telescope, robotical one, which can observe asteroids, natural and artificial satellites, and also solar activity, space weather. When we are dealing with asteroids, when we are looking to the sky, what we will see? If we observe just a piece of sky, we will see that point-like source. Major part of the observations are devoted to the point-like source. And this is fantastic because we astronomers, we have just few photons, just a point-like source, and we need to build around this information a real world. I mean, our imagination is without limit, but we need to be careful because our imagination needs to fit the reality, physical reality. In this image you have, but I don't know why it doesn't work. It's frozen. This is a PDF. Is this a PDF mode? Okay, never mind. Here in this image, usually it is a GIF image. It is an animation on which you can see the point-like sources, stars, maybe extended sources, galaxies, and behind these point-like sources, you will see some sources which are moving, and from some of them, here, and here, you will see there are point-like sources, but they are moving. And from some of them, you will see some segments like that, which are also moving. This means that the objects are from the solar system, and they are moving because there is a differential movement, apparent movement. These are objects from the main belt of asteroids, between Mars and Jupiter, and because you have an exposure time longer enough, you, instead of having a point-like source for the objects which are very, very close to our planet, we will see segments. So this is a small object which are passing very, very close to the Earth, and what we are doing is to observe all this, to measure all this, and also to find the position, and also to build ephemerides for such kind of objects. I will just make also an advertising, because we astronomers, we are interested by observing from the ground, and our paradigm now is what we call the technical evolution. We need to know that there are facilities on the sky in the neighborhood of our planet. I am speaking here about the satellite constellation, artificial satellite constellation, and this is an image on which you can see the the traces of Starlink satellites, and this is very, very bad for our science. From the ground, it is very, very difficult to understand how can we avoid this. And there is a group of work, instead the COPUOS, United Nations, COPUOS, Peaceful Use of Space, for dark and quiet sky. And people are, astronomers are worried, but also politicians should be worried about such kind of problematics. Here you have an image of how crowded is the neighborhood, the environment of our Earth. You see the geosynchronous satellites, but also a lot of satellites in the neighborhood at 300, 400, 600 kilometers of altitude. As I said, we can use this kind of observations of asteroids to build ephemerides, to know when to observe and when they are feasible to be observed. And here you have an international campaign organized by also a group inside UN COPUOS called I1, International Asteroid Warning Network. A lot of astronomers, a lot of observers who observed this object, 2019 XS. This object has a barbarian word, so name 2019 XS. Who named an object like that? We astronomers, we are named such kind of object with the name, the year, and also some letters. And this is the provisory name. This also should be a GIF, an animation, but I don't know why it doesn't work. Then, why we are studying asteroids and how can we develop our problematics? You must notice that our Earth is all the time in interaction with interterrestrial matter, and we in the atmosphere we will see a lot of falling stars, a lot of material which burn during when entering into the atmosphere. Here you have a network of all-sky camera. Here is a network, an all-sky camera. The network is called FREPON and started in France in 2016. And now this network counts more than 250 all-sky camera spread in Europe, but also in the world. And this is what we developed in Romania, the eastern part of the network, the largest and the eastern part in the eastern part of Europe. And why we are using this? To find eventually meteorites and also study them in the laboratory. And here you have a beautiful example of such kind of work on which we observe an object on the sky. This is the object, 2023 CX-1. This object was observed 7 hours before the impact with the Earth. And the monitoring said that this object will fall somewhere between England and France. Hopefully, this object falls in Normandy, in France. And what you see here is the, let's say, science participative in France. So social science, you can have a lot of enthusiastic people who can go and search for pieces of such kind of object, an asteroid of about 1 meter in diameter, and you see here one of the largest pieces that was found during this campaign of recovering the object. In fact, why we are doing here? We are doing this because, as you know, the asteroids are could be observed from using the space mission, but also this kind of facility is quite limited because you need to have a lot of funds in order to send instruments and space mission to follow and to see how the asteroids are composed and how the asteroids are made of. So you have here the largest, two of the largest asteroids and some other which were visited by space mission recently. And here you have something observed in the laboratory. As you can see here, the scale factor is 1 centimeter, and you compare this with object with 500 meters and even 1,000 kilometers. So we need to find such kind of link. As you can see from the laboratory, you have such wonderful pieces of metal together with rocks, but it is hard to find all the clues or the hints in order to link such kind of objects. But it is very, very important before sending a space mission for mining or for future space industries or for future suppliers for interplanetary mission. It is very, very important to know, to have all the information that we can find from the ground. I am sorry, I am very long. This is my problematics. I am dealing with large facilities. I am dealing also with spectra. What you have here are just spectra of asteroids, and each of them tell us a story. What is the composition at the surface of the object? You have several objects, and each point of such kind of let's say, segments represents something vital, essential for finding clues in deciphering their history. So I am a spectroscopist. I was working with this during the last 20 years, and also such kind of activity is doing in a network. In fact, I will just present this one and also this one. Running out of time. As you can see here, the Asteroid Day, in terms of astronomy and society, is present into our activities. Thank you so much.
I think we'll skip on questions for now. If you have any questions, you can ask during the break. Thank you so much for this exciting presentation. The next speaker that we have, we're grateful to have him here. Thanks to the generous support from the Embassy of Switzerland here in Luxembourg, which made this possible. We have Dr. Simon Grimm from ETH in Zurich, and he did his studies in Zurich as well, computational studies, computational sciences, and then he was part of the supercomputing team at Bern. He then went back to ETH Zurich and started looking at solar system dynamics. He is the main author of what's called the Jenga code, which is used by various research groups worldwide. I tried to understand some of the terms, but they were a bit too difficult for me in terms of something like opacity calculations. His major achievement, I think, was determining the masses of 7 of the TRAPPIST-1 exoplanets. Correct me if I'm wrong. And he collaborates at the moment with the Lowell Observatory in Flagstaff in Arizona. And today, he will talk to us about some really interesting stuff, which is fast solar system orbital calculations. Please welcome Dr. Grimm.
Yeah, thank you very much for being here. Special thanks to the Swiss Embassy. It's a great pleasure to giving a talk here, and hopefully it will be interesting. So as heard by the introduction, I will tell us something about the challenges in actually calculating orbits in the solar system. So that can be...
Speak to the speaker because this is live. Closer to the speaker.
Okay, thanks. Hope you can hear me. So I will tell you something about the challenges in calculating the orbits of any bodies in the solar system. So this can be small bodies like asteroids, but can also be orbits of planets, and then later on also exoplanets, which are planets in other systems, not in our solar system. So if you look at the solar system as we know it, so this is an artist impression. And let's see if I can, so we have one star, that is the sun, which is at the center of the system. Then we have 8 planets. We used to have 9 planets, but one got degraded. So we have 8 planets. And then we have a few hundred of moons. So these are satellites orbiting around the planets. And we have more than 1 million detected asteroids, and some few thousand comets, which also come close by to the planets sometimes, and we can detect them. So this is an artist impression here, and here you see how it looks in reality. So we see the planets and the inner planets, so that would be Earth here. We have Jupiter and Saturn, and so between Mars and Jupiter we have this large amount of bodies which are the asteroids in the asteroid belts. And we also see like 2 families of so-called Trojans which orbit the planets in so-called Lagrange points. So this is the picture that we have today, but what we will see next year. So I should go to the next slide. Okay. That was one too fast. So next year we will have a very interesting new telescope operating. So this is the Vera Rubin telescope, and this is on construction, and that's how it looks. And this one is the camera. So that's not the telescope. This is really the camera itself. That's the largest camera ever built. And this telescope we expect to detect more than 10 million new asteroids. So this is very fantastic, but it also gives new challenges because we have to recalculate the orbits of 10 million particles. And every night we have new detections, and we have to recalculate again and again the orbits, and that is computational very, very challenging. So we have to use the best methods that we can imagine, and we have to use high-performance computing actually to achieve that. And so this is also why the Lovell Observatory approached me to hopefully fulfill these demands. So just to summarize very, very quickly what these challenges are. So this is a system with one star, and we have 4 planets around them, and we want to calculate the orbits. So we know that there is no analytical solution to that. So there is no one equation that we can solve because the problem is chaotic in nature. So we only can do that by numerical integrations. So every planet interacts gravitationally with each of the others, and we only can do like very small time steps, and then we have to calculate the forces again and again. And there is only by computer codes you can achieve that. So imagine like we have a few other planets around there, and then the terms of gravitational forces between all of the bodies grows immensely. And imagine that there will be 1 million particles or even 10 million particles, and we have to calculate the forces between all of them. So that's why this computationally very, very expensive. And this gives me to these overview slides about the long history on computing method. And very interesting, like the very first computer codes, or not computer codes, were more than 3,000 years old. So already the ancient Babylonians had some numerical methods to calculate the position on Jupiter on the sky. So then over time it gets refined and culminated certainly by Kepler in 1600s to come up with the first physical laws, like how to approximately calculate the position, but it was not possible to do that accurate enough. So that's why we needed actually numerical methods. And the first numerical methods were carried out by human computers. So this is a collection of people, mostly there were women sitting in a group, and they were distributed by tasks. So they had to solve equations and gather them together and advance the orbits of planets. So that was a lot of human work involved, and then which nicely what got replaced by the first supercomputer. So this is the Cray 1, which is one of the famous, which allowed then for much faster calculations. But of course, the problems also grow more and more, and it got more complicated, so we needed special hardware. So one example is the grape computer, which solves the equation of gravity directly in hardware. So there is no equation to solve, but there's one cycle in the computer clock which solves the gravitational problem of two bodies attracting each other. It turned out that this approach was a bit too expensive, and today we are using GPUs, graphics computing units. Actually, these are the same cards as many gamers have in their home PCs, or it's used for data analysis, and we use them to do very heavy parallel computing to solve the n-body problem. And so this would also be an animation. So maybe if the technicians could click on it, let's wait a few seconds. That didn't work, so that is the next slide, but that's no problem. If we can just go with the mouse on the picture and eventually click on it. So I think this is not helping, so we continue with the next slide. I'm sorry for that. So this is the asteroid belt in more resolution, how it looks. And there are few things that we recognize here. So one thing is that there are gaps in between. So there are rings with no asteroids. And if you plot the same in a diagram, which shows here the distance to the sun, and this is the inclination, like this is the height of the system, then we see also that there are clusters of objects. And so we want to understand where these clusters come from. So we can understand that these gaps, these are the so-called Kirkwood gaps, and they are caused by mean motion resonances, which I will explain in the next slide. And the clusters here, these are caused by collisions between asteroids. So if the asteroids also collide with each other and destroy them and create a large cloud of fragments that we see here. And this cloud of fragments can also reach the Earth after some million years. So orbital resonance is a configuration here sketched with two planets, and both of them orbit the star. The inner planet orbits faster than the outer one, and in some configurations it happens that like these two planets are aligned like every other orbit, and they will cause like a grow of the gravitational attraction in this direction and giving like a scattering effect. So this is known as the 2-to-1 orbital resonance, and then there would be higher orders, 3-to-1, 3-to-2, 4-to-3, which cause then these gaps in the asteroid rings. But gravity is not the only force that we have to take into account. Of course, we need general relativity. General relativity causes the elliptic orbits to precess, like they change their orientation over time. So we need to take that into account to calculate the orbits correctly. Very important is also the shape of the planets. So the Earth is not a perfect spherical planet, so it has this very potato-like shape. So if there is a very close flyby from an asteroid, this matters. And so we have to consider for this non-spherical shape, so these are called the J2 and J4 terms, and we also have to take those into account. Very interesting and very important is also the Yarkovsky effect. The Yarkovsky effect is a thermal force, so you can imagine that the planets are heated by the sun in one direction, then the planet or the asteroid rotates and emits the force into another direction, and that causes a force on the object. And that is important for the long-term motion of the bodies. This is an example how that works. So this is a simulation of a collision between two asteroids. So this is illustrated here by the asteroid Hebe 6 as what would happen if this collides with another asteroid. So this is the distance to the sun and the inclination. Then we have Earth here. And here, this is the collision, and all of the black particles are ejecta fragments which are caused by this collision. Then we see that we have these resonances from Jupiter showing up here, and the resonances move the particle on highly inclined orbits. Then we have gravitational dampening, so the particles move downwards, and they reach the Earth here. Like after 5 to 10 million years, the planets actually collide with the Earth. And the Yarkovsky effect is important because the Yarkovsky effect constantly moves particles from here slowly outside and inside into these resonance regimes, and constantly new particles reach the Earth. So there will be a long meteorite flux and eventually particles reaching the Earth. And so we can predict when we observe collisions, when we expect many, many particles actually to impact on the Earth. And the same mechanism also happens if we study the formation of the solar system itself. So this is also a simulation of the creation of the solar system. So here we have 4 sets of different resolutions. But we start with a disk of so-called planetesimals. And planetesimals are actually very similar to the asteroids that we observe today. So we have a disk of planetesimals. They all interact gravitationally. We have the resonance structures again. So the resonance move particles on this very funny orbit to the inner part of the solar system. Here, the Earth is formed as a protoplanet, and constantly new material is delivered to Earth until it reaches its final form. And then we are left with a few terrestrial planets here in this system. They are still colliding, and we only have 2 planets, but we have here the asteroid belt as a leftover. And so the asteroid belt also is a measure how good our theories of the understanding of the formation of solar systems are, because we actually have to reproduce what we also can observe. And that is also a very interesting aspect. So I come to the end, and these are the main conclusions. So the calculations are very, very challenging. So we have to use the best methods that we can get, the best hardware that we can get. But they are very, very essential for entire astronomy. And the asteroid belt is also a key to understand the formation of the solar system itself. And with that, I want to thank you very much for the listening.
Does anyone have a burning question? A really burning question. Otherwise, we'll leave it till afterwards. Okay, thank you so much indeed for bringing us slightly back to time. Our next speaker, I am delighted to say, is the first speaker that we have from the Middle East and North Africa. Her name is Hera Al-Mazmi. She's a space science researcher at the United Arab Emirates Space Agency. She graduated from the University of Colorado with an MSc in Aerospace Engineering in 2020, and from the Virginia Commonwealth University with a BSc, initially before that, Mechanical Engineering with a focus on nuclear engineering in 2016. She is a program scientist at the EMA, which is the Emirates mission to the asteroid belt, and is a member of the Emirates Mars mission science team. She's also interested in studying the link between Mars water vapor during dust storms and hydrogen escape to understand how Mars is losing its atmosphere. Please welcome Dr. Hera Al-Mazmi. Who will describe their mission to the asteroids belt. Thank you so much.
Thank you. And thank you so much for having me here. I'm happy to be sharing our mission with you to celebrate Asteroid Day. So the Emirates mission to the asteroid belt is a follow-on mission on the Emirates Mars mission, which is the HOPE probe that has been observing the atmosphere of Mars since 2021. So the main goal of that mission was to improve the technology and research capabilities within the UAE and to encourage people to go into science and engineering in the United Arab Emirates. And this mission is hoping to follow up on that and to continue that path. But it's also adding on the aspect of increasing the private space sector and growing the private space sector in the UAE, which is why there is a private sector aspect to this mission in which we're hoping to have at least 50% of it be developed by private companies and specifically the lander, which you'll see later is related to this mission, is going to be 100% developed by private companies. So this mission is going to be flying to 7 asteroids in total. It will be flying by 6 asteroids in the main belt and rendezvousing and deploying a lander on the 7th asteroid. Again, this is just contributing to the growth of the space sector in the UAE and the knowledge transfer to the UAE in space and in planetary science. And the mission's spacecraft is called MBR Explorer. So this is just a general overview of what the spacecraft is. It has heritage from the Emirates Mars mission bus. It has 5 instruments. This is incorrect, but we'll see the 5 instruments later on. That are going to be doing science at each of the flybys and during cruise. And the propulsion systems are 2. So we have a chemical propellant and a solar energy particle, SEP propellant, so an ion thruster or an ion propellant. And in terms of, we have 2 large solar arrays to deal with the distance from the sun. Because we're going to the main asteroid belt. And this is just general information about the spacecraft mass, which is 900 kilograms approximately. So moving on to the asteroids that we're going to be visiting. So there are 7 asteroids. The smallest is around 2 kilometers in diameter, and the largest ones are around 50 kilometers in diameter. Some of the named ones are Westworld, Chimera, Rockox, and Justicia. And this is the timeline of the mission. So the mission is planning to launch in 2028. We have a Venus gravity assist and an Earth gravity assist, and we'll be flying by our first asteroid in 2030. And then we'll also have a Mars gravity assist, and finally we'll get to our final asteroid in 2034. And we'll rendezvous with it and deploy the lander later on. So another thing that's unique about this mission is that it's both a science and a space resources mission, and so we have goals that relate to science and space resources that we'll go over briefly, but it's important to understand that they share a common set of investigations and a common set of instruments and payload. So in terms of science objectives, we're interested in understanding the origins and evolution of water-rich asteroids, and we're going to be doing that by studying the diverse asteroid surface, and we go back to diversity of the asteroids because we'll look at some diverse asteroids that we'll be visiting in the main asteroid belt, and trying to understand its surface, interior structure, geology, and thermal features. And then for space resources objectives, we're interested in assessing the resource potential of asteroids and preparing the way for future asteroid use. So this is more for future exploration missions where we're hoping that future missions can make use of the information that we're going to be gaining about the content of resources that are going to be found on the asteroids that we're going to be visiting and the potential for extracting those resources from asteroids. So these are the 5 instruments on board our spacecraft. So the first is an infrared spectrometer. This has heritage from the Emirates Mars mission as well. We have a very similar instrument that was flown on there, and that's going to be looking at the surface composition and the temperatures and the thermophysical properties. We have a visible camera, a visible narrow-angle camera, and an infrared camera, and those will give us geologic context for shape modeling and surface aging, and also the thermal camera will give us surface temperatures and rock abundance and porosity of material. And then the third instrument is the MIST-A instrument, which is a mid-wave infrared spectrometer. This is an Italian space agency contributed instrument. So they contributed the instrument to this mission, and we'll be flying it on our spacecraft. And it's going to be looking at surface composition, including water, ice, organics, and ammoniated compounds. And then finally, we have a relativistic electron-proton telescope, which we recently announced as being part of this mission. It's called Reptile 3, and it's going to be looking at the solar energetic particles, and it will be turned on during cruise as well, which is unique about this instrument because it's the only instrument that we'll be getting data from during cruise as well, since we'll be traveling for such a long time. So back to our asteroids, and going back to the previous presentation by Simon, who explained it wonderfully, the asteroid belt is important for us to understand planetary formation. So by visiting the asteroid belt and studying these asteroids, we can better understand the origin and evolution of asteroids and the origin of water in general. So that's what we're hoping to do, and this is why we chose these specific asteroids. You can see a similar plot to what was presented previously, but this plot is showing the distance from the sun and the inclination and the y-axis, and it just shows you where our asteroids are, and that they come from different families. So by visiting these asteroids, we're also understanding the family as a whole, not just one asteroid. And finally, the rendezvous target is especially interesting because it's one of the reddest known asteroids in the main belt. So by visiting it, it would be very interesting to understand why it's so red, and it would solve the mystery of its redness. And one of the recent updates that we've had for this mission is we conducted an occultation campaign, or a stellar occultation campaign, to try to better understand the shape of our rendezvous target, which is Justitia. And an occultation campaign is basically just us looking at one star that we know the asteroid we're interested in is going to be passing in front of, with a bunch of telescopes, and that constrains the size of the asteroid as it passes in front of the star, as we measure the time that the star's light goes out, basically, and that gives us information about the width of the asteroid. So we did that with 34 stations, and we're hoping to publish that information on the asteroid very soon. And that brings us to the conclusion of this presentation. So in general, that's what our mission is, and we're very excited to join the asteroid community with this mission and to share science with the world.
Thank you so much. You really have brought us back to time. And I'm really, does anyone have any questions?
Congratulations first for your challenging program. As you want to target 7 asteroid families, don't you fear that your probe will enter in collision with these asteroids of the family?
Oh, so the asteroids are pretty well spread out. So even though they're within families, they're still far away from each other. And we've factored that in, and we're hoping that there won't be a collision. Yeah.
Thank you so much indeed for that. I was listening to those names of the families, and I thought it was something like Costronoso or Mafiosi or something like this. So it's fantastic names. Thank you so much, Howard, for that really exciting talk. Our final speaker before we take a short break is Alex Karl. Alex is a German space engineer working in the astronaut office of ESA at ESA's European Astronaut Center. He is an experienced ISS flight operations engineer with over 1,000 on-console shifts. He is directly interfacing with and supporting the astronauts at the ISS as well as ESA astronauts before, during, and after their missions. Alex is active, and that's how I know him quite closely recently, in the planetary defense community, protecting Earth from asteroid impacts, mainly in public communication, education, and outreach, something we share in common. He's currently the co-chair of the biennial IAA Planetary Defense Conference, the PDC, and the chair of the IAF Technical Committee on Planetary Defense. And he is here today to talk to us about the conference next year in South Africa, the 9th IAA International Planetary Defense Conference. So please welcome Alex Karl.
Thank you, Maher. Can you hear me? Yeah, that sounds right. Okay, welcome everybody. I'm happy to be here. Yes, I would like to talk to you about the upcoming Planetary Defense Conference. Quick show of hands, who here has been to a PDC or heard about a PDC? 2 people, well, 5. Okay, great. Talking to the right people then. So it's a conference where the planetary defense community gets together. That happens every 2 years. Our next meeting will be in May of next year in Stellenbosch in beautiful South Africa. And just to give you an idea what the PDC is about, so our last meeting happened last year in Vienna. The very first meeting was held back in 2004, so this is now the 11th in the series of conferences, and the 9th that is held under the auspices of the International Academy of Astronautics. And in Vienna last year, we had 275 in-person attendees, about 200 remote participants at any given time, and a total of almost 1,000 remote viewers representing over 60 nations. We had about 100 oral presentations from experts talking about the work and the results, and had about 150 poster submissions, out of which we had around 100 that you can see in the background there in the UN Rotunda. We are not limited to technical sessions. We also had a special event preceding the conference that was about the successful DART mission from NASA. You hopefully all heard about this one, where some of the people involved shared their insights and experience with the mission. And we had and that was open to the public as well, and we had a special screening of the IMAX movie Asteroid Hunters. The producer and director was there at the conference as well, and then after the movie was shown and was open to the public, they had an expert panel with the people who were actually in the movie. And we have student prizes for the best paper poster, so we very much encourage students to present their work as well. Here you just see a quick overview of our co-chairs. So currently we're 6. It sounds like a large number, but there's some generational handover happening there. So we want to make sure the conference is in good hands, and I think it really is. Looking towards the technical sessions that we have next year, on the right you see some images of the conference venue. I was lucky enough to visit a couple of weeks ago for a site visit. It's very nice, it's very well equipped. We're really looking forward for the conference there. And one thing I want to point out of the different sessions, it's just the breadth of topics. So it covers everything you want to look at when you find an asteroid that may be heading your way. So it goes from just international developments, what are the different space agencies doing, there's discovery, there's characterization, we have deflection and testing, we have mission design, we have impact effects, disaster management, public education, outreach, as you can imagine, and as we've seen with COVID, how you communicate something is very important. The decision to act for our, in various fields, from political, legal, social, economical aspects, we're happy to merge, in a way, the POFIS T-X years workshop that is held every year. So we give them a session this year, and we're looking forward to hear some updates for the initiative for the International Year of Planetary Defense. That will happen in, so for those who may not be aware, so in Friday, April 13th, 2029, the asteroid Apophis will have a very close flyby of Earth. No worries, nothing is going to happen. So no impact, I mean, but we'll be so close it's visible with the naked eye. So this is a great outreach opportunity. And the International Year of Planetary Defense aims to take advantage of that. And there's currently some process ongoing with the UN to declare that as an international year. And there's a lot of outreach associated with that. So we're looking forward to an update. We do have also a wide variety of panels. This is the topics from last year, just to give you a taste. We haven't selected the panels for next year yet, but one is related to the exercise, and I'll speak about that in a minute. We have national security preparedness, everything, well, disaster management, we had communication with the public, and as well legal and policy issues. So as you see, it's a very broad field. And this is one of the things I personally think is great about planetary defense. It's not just for engineers and scientists, it's really for everybody. And what fascinates me every time is that an asteroid impact is the only natural disaster we can not only predict, but also prevent, given enough time. And we cannot say that over any other disaster. So this is really exciting, I think. And talking about the asteroid threat, since 2013, we started introducing fictitious, that's a key point, fictitious, but realistic scenarios that threaten different parts of the world, and then as we have the whole community there together, we can make sure to see how ready are we for a real case. And it is usually great fun. It is also, last year, for example, being at the UN, we took advantage of to have actual decision makers there, to present them the problem, to present them the options as far as we know them, and because they in the end are the real people who have to make the decision. Do I allocate money for a 10% impact chance for a $100 million reconnaissance mission, or which in 90% of the cases you wouldn't need to spend? Or do I wait and then I have to spend a lot more money, or it may be too late? So it's a very dynamic and interesting exercise. One thing, okay. One thing, so it covers not just the detection and where it might hit, but also potential deflection and impact scenarios. And one thing we're doing this time, we're publishing the scenario online before our call for papers opens. So anybody who's interested to work that particular exercise thread topic is welcome to do so and submit a paper dealing with that topic. Of course, just as Asteroid Day here in Luxembourg, we couldn't run these conferences without the help and support of our sponsors. This is just an overview of the 2013 sponsors and supporters. Thank you again. And for the 2025 conference next year, there's still sponsorship and exhibitor opportunities available. So if you're interested, have a look at the website or come see me later, and then I'm happy to give you more details. The key dates. One more minute, please. So the key days, on the 1st of August, we plan to publish the asteroid exercise details, then followed by the call for papers. Early September, we open registration in the abstract submission. That runs until end of November. Then mid-January, we hopefully have performed all the reviews and informed the authors. And then until the day before the conference, you can submit your full paper. And then in early May, hopefully, we'll see you in South Africa. Just a quick overview. So we have 5 days with 1 day in advance. We have an extra special day for the poster viewing. We have social outreach events again, and potentially some post-conference leisure tours, as the destination is quite nice. And yeah, on behalf of the local organizing committee, I'd be happy to invite you all to South Africa next year and join the Planetary Defense Conference. Thank you.
This is perfect. We're back exactly on time. Thank you for that. Does anybody have any questions for Alex here? You can ask him any questions if you want. It doesn't have to be on PDC. You can ask him. You can ask. You can ask about how he talks to astronauts and their families. And anyway, we have the opportunity to talk to him later on when we'll be down at the Museum of Natural History Museum. Thank you so much indeed for this. We have a break for like 10 minutes. If you want to stretch your legs, have a drink of water or something. Then we come back for the second part of this. Please be back in 8 minutes. Or you can just stay here if you wish. Can you please take your seats? Thank you. Okay, just a bit about the program after this next speaker and the panel. We hopefully will be finished here by 8:15, and then we start migrating towards the Museum of Natural History down in the Grund in Luxembourg. When you get there, we have drinks, cocktails, we have something to eat, and you have the ability to actually wander around the museum. There's a big exhibition at the moment. It's called the Asteroid Mission. It really is a fascinating exhibition in there, so please try and take advantage of that. So the next speaker is Edgar Milic, and Edgar is a really, I mean, I looked at his CV and I started jotting things down, then I found myself writing like 2 pages. And I thought, no, I'd better cut it back. And he's a really passionate space enthusiast, and he has roughly more than 20 years of experience in space, technology, and governmental sectors. He currently holds the position of Luxembourg Country Manager for GomSpace, which is a global leader in small satellite solutions. Before joining GomSpace, he was the CEO at OHP LuxSpace, and he had roles in business innovation, corporate development, business development, and venture capital funding, such as at SES Satellites. He worked as a project manager for Earth observation and simulation projects at GMV, and served also as an officer in the Italian Air Force. He holds a master's degree in aerospace engineering from Rome University La Sapienza, an executive master's in business administration from IE Business School, and certificates from Harvard Business School in SEED and many other institutions. He is a mentor for startups, a former advisory board member of the Seraphim Space Fund. He has lectured at Luxembourg University in space business and entrepreneurship, and is a father of 3 kids as well. That's the proudest moment of his life, I think. He, as I said, he is at GomSpace, which is a leading manufacturer of small satellite technologies. He will tell us about that. And we are grateful for GomSpace for part funding this evening as well. Thank you very much, GomSpace, for doing this. So without further ado, I'd like to ask Edgar to come and give us his presentation. Please welcome Edgar Milic.
So with this presentation, the expectations are now high, so I'm going to disappoint you all. I'm sorry for that. So you can all hear me well? Very good. So, dear space enthusiasts, esteemed colleagues, ladies and gentlemen, first of all, good evening. As it was already said, my name is Edgar Milic. I have the honor of representing GomSpace, a small satellite solution provider, one of the leaders worldwide. And I think that today what I'm going to talk to you is about a story. And I'm thrilled to tell you the story of our passionate engagement into one of the most remarkable missions that we are going to be seeing in the next few years, starting October 2024. And this mission is going to be in relation also with another mission that was mentioned earlier today, which was the DART mission. So today is about the Hera mission and Juventas roles and the roles of the CubeSats in that one. So this story actually starts with one memory of mine. And that memory goes back to a definition of Earth that probably many of you have heard, which is from one of the most visionary scientists that we have ever had, which was Carl Sagan. And when he looked at a particular picture of Earth, he defined it as a pale blue dot, because it was in the middle of an ocean of other things, and it was very small. Well, what I certainly realize even more when I'm talking now with my 3 kids, as was said also before, is that when they ask questions, definitely we are living in this Earth of ours, which looks magnificent, right? And it is magnificent. We are surrounded by oceans, by high mountains, by the Amazon forest, which is all a repository of the resources that we need and are keeping us alive, without talking about the atmosphere and the sky. All that seems to be so magnificent, and it's so fragile. Earth is really put in a place in the solar system, which is special and challenging at the same time. I think one of the speakers before was talking about the millions of asteroids that are present in the solar system. And he was showing one of the pictures which was really amazing, which was showing the density of all those objects at some point in time. This picture here is showing something similar, which is how the Earth is surrounded by all those things. And there are comets, which have been revealed as being carrier of organic material that could be at the origin of life. It's surrounded by other asteroids. And it is their place in its orbit, together with many other things. In this picture, there is another thing that is placed as well. And it's that little object, Didymos. And this is important in our story. And that's where we turn to now in order to go on in telling that story. This is Didymos. Didymos, I tell you already now, it's special. Didymos has a characteristic of being a binary asteroid system. Binary means that it's not alone, right? That's probably what you have already guessed. So Didymos is really composed of 2 objects. Didymos and that little small ball that you see there, which is called the Dimorphos. Both are special. In their composition, maybe they are special. And we will discover that even further as we will talk about the next mission. They are not that big. So Didymos is about 780 meters in diameter. Dimorphos is 160 meters in diameter. They are fairly small, right? And their composition is probably, in the case of Didymos, is pretty sure, is done of minerals and some metals. In the case of Dimorphos, it will be understood in the course of time. But there is something that that started attracting the attention. It was this binary nature and the possibility, therefore, to launch missions that could study the interaction between the 2 bodies in a very special way. That was the origin of the concept of the DART mission. The DART mission is a mission that started in November in 2021 and was supposed to get close to the Didymos system in order to execute surveys, understanding better about it, taking pictures from the distance, and do something very, very particular. This is one of the last pictures that was taken of Dimorphos. Before DART, the double asteroid retrajectory mission, test, before DART hit at 6.6 kilometers per second Dimorphos, in order to see if we could change any of those characteristics, and also to be able to see if there was something more inside the asteroid. So when I asked today, and I had some pleasant conversation these days with some colleagues present, when I asked today, okay, but then what has changed? In many cases, the answer is, we don't know. There is one thing we know. Before hitting Dimorphos, Dimorphos was circling around Didymos at an orbital period of 11 hours and 55 minutes. After the hit, that value was reduced by more than 30 minutes. So we effectively made something quite unique. We changed the trajectory of an orbit, of the orbit of a body of the solar system by a man-made object. This is a remarkable achievement. And then what else has changed? That's where it comes into play, another element of our story. The Hera mission, together with the Milani CubeSat and the Juventas CubeSat on board, will launch in October 2024. The mission of those 3 probes is going to be to going around the system of Didymos and study what has happened fundamentally. Again, when I'm asking the question, the answers are, there is certainly still one piece of Dimorphos, but we don't know how big the crater is. We don't know how much of it has been truly revealed. We don't even know today if the interior of Dimorphos is a solid rock or is something else. That's why there is a lot that we need to do with this mission. The Hera spacecraft, built by OHB with the collaboration of the 2 CubeSat provider, Tyvak and GomSpace, is going to be launched on a Falcon 9 SpaceX rocket, and shortly after that it will be separated from the rocket, and is going to go into a trajectory of about 2 years in order to reach the Didymos system. There is a set of phases that are going to be encompassed there, and I will go briefly through each one of them. First of all, after launch, there will be the cruise to the Didymos system. There will be also a Mars flyby in a part of the trajectory in order to gather energy and speed and reach the final destination of the Didymos system. The first thing that will happen when we arrive there is going to be the deployment phase, the early characterization phase, where Hera, without having separated from the CubeSats, will start doing an early mapping of what the system is. This is going to be very useful to then plan for the next steps in the mission. There is a lot that we don't know at this moment in time of what the Didymos system looks like. The second step will be the separation of the CubeSats. They will be released, and we will talk a bit more about that in a few minutes. Then there will be a detailed characterization phase, and that will be done with the collaboration of the 3 spacecraft one another, each one with their own respective instruments. In the case of the CubeSats, and I will explain a bit more later on, one of the CubeSats, the Milani one, will study more the exterior of that. What we will do with our Juventas spacecraft is going to look more at the internal part of the asteroid. Later on, there is going to be a more detailed investigation by Hera that will approach further the Dimorphos spacecraft and will do even further analysis. You should imagine that these spacecraft have visual instruments, they have optical instruments, RF instruments. So there is a collection of elements that I will talk about later that is really complementing each other. There is a last final step, and somebody was cautioning me on that earlier in the week. But there is one final step. The 2 CubeSats will attempt a soft landing on Dimorphos. And of course, you could imagine when I'm asking an engineer, so how soft is going to be? The guy is looking the other way. But the core point is that we will attempt that, because achieving that is going to be marvelous in permitting us to understand even more about the characteristics of it. Talking to Patrick Michel earlier in the week, he was telling me that most of the tests that has been done until now have revealed that when you get to an asteroid and you think it's solid, then actually you're going through something that seems to even vapor or something like that. You're getting through that. Well, we hope to discover things like that when we are trying and we are attempting the landing of both CubeSats on that. In this simulation here, you will see what is the interaction between the parent, Hera, and the children, the CubeSats. Both of them are going to reach the system in an integrated configuration. But the release will happen once we are there, and it will happen in 2 steps. The first one, the CubeSat will be released but still attached to Hera. And that is extremely important. A parent must always communicate with their kids. I think I'm talking to myself somehow, but nevertheless. And you should make sure that the instruments that you put on board are indeed making that function and making that efficiently. Because the kids at some point in time will go out and will start studying things for themselves. And in our case, it's certainly true. We will deploy our solar panels at that point in time. We will do the activation of all the instruments, the testing of all the instruments, and we will deploy like those antennas which are part of the instrument that we have for the low frequency radar. After 2 weeks, the Milani CubeSat, the one manufactured by the colleagues from TIVAC, is going to be released as well. The delay between the two steps is really to allow enough operation in the early phases in order to make sure that Juventas is properly starting its operation. At that point in time, both of them will be deployed and they will start the mission, relaying data back to the parent, to the mothership. The CubeSats do not have the capability of relaying data back to Earth. They have to talk to the mother in order to get that message back. We would always love that this happens also with our kids, right? This trio of spacecraft, as I said, is quite remarkable. They complement each other with a number of sensors and characteristics which are really making that even more powerful by the combination of them. Our Juventas is no common CubeSat. We are extremely proud of what we have done here and how much the engineers, some of them present here tonight, and that probably could be the target of your question, because from me you will get only dumb answers. They can explain you what are the characteristics of the sensors on board. I can only give you a brief span of that. There are 3 core set of instruments that we have on board Juventas. As I said, we will concentrate more on the interior of the asteroid, more than the exterior, which will be more the mission of Milani. For the interior, we have loaded on board a low-frequency radar, which is manufactured by a company in Luxembourg, Emtronics. The low-frequency radar has a special characteristic as an instrument. It permits us, from a distance, to look below the surface of the body that we are observing. And therefore, with that, we can understand the distribution of mass, deducting the material, possibly seeing voids, to the point I was making before after my conversation with Patrick. The second instrument that we have is a gravimeter. With that, we will be able to measure the one that you can assume is being microgravity. We are talking about a 160-meter diameter body that does not have a huge gravity, a little more than myself. And with that gravimeter, you can measure this field. And even more we will do in the moment when we soft land on Dimorphos. That's why it's even more important to be stably on Dimorphos and then continue the campaign of measuring with the gravimeter. At that point in time, and even before, it's going to be very important to have good accelerometers on board, the gyroscopes on board. So instruments that are permitting you to maneuver, approach Dimorphos, land, and once there, also use that in order to understand the mechanics. All this campaign of sensoring is going to be extremely important to understand the origin of the system, the relation that the two bodies have had, and in some cases also understanding if there are very useful and very interesting resources. We know that some of the bodies in the solar system, some asteroids, may contain metals which have an enormous value. And that's true for platinum, and I have colleagues who are hoping to find diamonds, actually, on Dimorphos. I hope they bring them back. Now, in these CubeSats of ours, and I'm sure the colleagues from TIVAC can testify, we have come a long way. 20 years ago, there were people that were saying that they were basically useless for these kind of missions. Today, we are executing missions going to an asteroid with those instruments. Inside a nanosatellite, and this is by and large the size of the Juventas spacecraft, you have a remarkable set of elements and components. You have propulsion units, you have advanced reaction wheels, you have antennas of all kinds, system-defined, software-defined radios of all kinds, battery packs, and also instruments like the one that I was describing very lightly before. Instruments which are very sophisticated also for planetary and solar system exploration. At GomSpace, we really take pride of the amount of things that we have developed across these almost 20 years of operation. We estimate that roughly 1,000 of our products are put into orbit every single year. We sell our products in 55 countries, in more than 55 countries worldwide. And we have many years in orbit and many missions that we have executed. This comes by the simple nature of our company, that we have realized over time that what we take pride on is to help teams across the globe achieving their goals in space. And this is really what is driving us forward. Now, in this last video, you will see the main phases of the Hera mission. And that will permit you to recapture a bit some of the elements of the story that I was talking about a few minutes ago. But I think that most of all, Hera, DART, the CubeSats, represents a great story of partnership and collaboration across the globe, across the ocean, in the US, to Europe. And there are always challenges, debates, like, so our projects, our space projects are apparently looking like all others. There is a requirements definition, there is meetings, there are debates, there are contracts put in place, there are more meetings, and then there are reviews, and then there are more meetings, and then there are troubles in between. And we overcome these troubles. And by overcoming these troubles and these challenges, we achieve things. So our job looked like many others. But the space engineer job is no ordinary job. What we do here is taking us at the fringe of what humankind can do. And if one loses that spark in doing this job, it's losing 99% of the fun and of the motivation for going forward. This is closing the loop with the story and with the looking at the pale blue dot. We can achieve protection of our planet by empowering humankind like we do in the Hera and the DART mission to make changes even in the solar system. And that's what makes us proud very much. Thank you.
Thank you so much for this really fascinating presentation. Does anyone have any questions? Any questions?
Out of curiosity, why did you choose the specific, was it binary and asteroid system to explore and further learn about?
It will be answered in the panel, because I think there are much more gifted people and knowledgeable about that, which is more the science team, which is behind the Hera mission. The selection of that, to the best of my understanding, has been that the interest of the system in general, already at the time of DART, was that being binary, it was a wonderful occasion to study also the changes in the orbital trajectory of the dimorphous asteroid. So by hitting that, you would have been able to determine the small changes that it has around the Didymos asteroid. And probably they will be able to elaborate later in the panel, so that's a wonderful question for the panel later.
Thank you. Any other questions? Yes, please.
If it makes a soft landing, if Juventas makes a soft landing and it survives, could you actually get some more data from the surface?
We can. I think that the important part of that is that the system, so Juventas and Milani has probably a set of instruments on board, will have accelerators, will have gyroscopes. In that way, by being on dimorphos, we'll be able to see how the body is moving. On top, the gravimeter is going to still working. And we will be in the closest point possible to dimorphos at that point in time to measure the microgravity. So all those things will still be working. Possibly the one that will not be useful anymore is the low frequency radar, because probably by the time that we are hitting that, most of the antennas will be gone, and I suspect that that will not be working anymore.
Any other questions? Yes, please.
Do the CubeSats have a possibility of retrieval and return of soil from the asteroid?
In this specific case, we are absolutely not doing that. So it is not, it is not among the mission specification. If you're looking forward, probably CubeSats, in my view, could be an instrument to retrieve but then to inevitably use a mothership in order to potentially make a return mission of some kind. But this mission certainly doesn't have it.
Edgar, you said that if anybody had any questions to the engineers, are there any here sitting in the?
Yeah, I'm sure they are scared if
Are
I
they
point
here?
at them.
Can you please
Yeah,
stand up, whoever the engineers
Well,
are?
we have the project manager from our team,
Yeah,
from our
please stand up
Juventas
there.
team
Yeah,
here.
I only ask this because,
yeah, but-
because I want people to be able to ask you questions afterwards at the, down at the museum.
Unfortunately for him, I just saw entering one of the most important system engineer of the mission, which is over there, José.
Yeah.
And so
Stand up, please,
you,
José.
you can certainly ask a question to José as well. But here in the room, you have a panel of people which are extremely knowledgeable about the Hera mission, the Juventas mission, the Milani mission. So we are represented from TIVAC. We have the European Space Agency present here, and Patrick Michel. We certainly can do that.
Thank you. Please join me in thanking Edgar for a fascinating presentation. I actually wanted to mention just a couple of things. Is that asteroid number 10034 is named after Miral Birlan over there, who was our first speaker. And asteroid number 7561 is named after our next speaker who's moderating the panel which is coming up now, and that is Patrick Michel. I'm sure most of you know Patrick Michel, but just in case somebody has been sleeping for the last 20 years, Patrick Michel is an international expert of asteroids. He's the director of research at CNRS at the Lagrange laboratory in Côte d'Azur. He holds many titles. He's a professor with a permanent affiliation, permanent affiliation with the University of Tokyo. He has over 230 publications. He specializes in numerical simulations of the impact process between asteroids and of their surface and interior, which is something really relevant to what has been asked earlier. He is for tonight as well, he is the principal investigator of the ESA Hera mission, which was launched, as we heard, in 2024. And he will simulate a panel over here, and they will talk to us about this mission, Hera mission, the latest news and the outlook. The people will be on the mission. Can you please come over, Patrick? Thank you. Please welcome Patrick here. Also would like to welcome Alan Fitzsimmons. Margarita Cardi, please. And Franco Perez Lisi. And before I hand over the microphone to Patrick, I'd like to remind those who are watching us online that this is a presentation of the Asteroid Foundation. It's a Space Lecture 2024. Thank you very much for joining us. Thank you.
Thank you. Okay, so good evening, everyone. So I'm Patrick Michel. I'll be the moderator, which is better because I'm very talkative. So if I'm a speaker, you are here for 2 hours. We are in live, we are broadcasted, and yet we didn't prepare anything because we know each other so much that we can have like a family discussion, if you want. So we're going to talk about Hera, and you have seen already with the presentation that we will have surprises because until now, each mission that we did to an asteroid showed us something we did not expect, each of them. And with the Hera, you could say, okay, we saw the images of Didymos and Dimorphos with DART, but DART made a mess. And therefore, Dimorphos will certainly not look like the images before the impact. And that will be, for us, the great source of excitement when we receive the first images. So we're going to talk about that. And for this, I've got Franco, who is from European Space Agency. He's a system engineer. He's in charge of the 2 CubeSats, Milani and Juventas. And he has been on the core team of Hera for 5 years. So long experience. And he's also following all the payload development. We got Margarita Cardi, who is TVAC International, number 3, which is very high because usually number 1 is in vacation, number 2 check the vacation of number 1, and number 3 start working. So she's doing the hard work, and she's the project manager of the Milani CubeSat, so at the head of the Milani CubeSat, which he will talk about, and she has a master's degree in aerospace engineering from University of Roma, La Spienza, right? Okay, and then we have Alan. So Alan, 20 years. 20 years. So he's a professor at University of Queen's University in Belfast, right? And for the story, all you talk about tonight, DART and Hera, started at the European Space Agency. So, of course, NASA did the first part, but in fact, the very first studies started the European Space Agency in the early 2000s, when both Alan, I, and other colleagues were asked by ESA to recommend priority mission to deal with this impact risk. And at the epoch, we recommended a mission called Don Quixote, which were at 2 spacecraft, one impactor called Hidalgo. For those in Paris, Hidalgo is another thing, but it was a projectile. And the spacecraft Sancho was the orbiter observing the outcome. So exactly the architecture of DART and Hera. And then, okay, the story is long, so I will stop. But then, because of our recommendations, it led to the initiation of the collaboration DART and Hera that finally took place. 15 years of fight that we share together. So, of course, Alan is involved highly in Hera. He's in the science management board. He's also an amazing astronomer involved in the LSST. We talked about the Vera Rubin, so LSST Vera Rubin. He's also part of the Atlas survey, and he was also part of the observers of this Oumuamua interstellar asteroid, which now is away, but very interesting. So thanks, the three of you, to be here. So to start the questions, otherwise I talk the whole time, I will start with Alan, because we had an interesting question. Why did we choose a binary?
Okay, so why do we choose a binary, and why choose Didymos and Dimorphos to go to with DART and Hera? Well, it's because, as Patrick said, when we first developed this concept 20 years ago now, we realized we needed probably 2 spacecraft, because at that stage we were going to go for a single asteroid. We would hit it with 1 spacecraft, but then we would need another one already there to measure the very small motion, the very small change in motion of that asteroid after we'd hit it with the first spacecraft. Because we cannot do that very accurately from Earth, and I know this because I've spent my entire career trying to observe asteroids and comets from Earth-based telescopes, and it is incredibly difficult to get the amount of precision you need. But then, somewhere along the line, I'm not sure which year it was in those 20 years, the idea came to measure a double asteroid. And that gives you, for particular asteroid, for double asteroids, that gives you an advantage. Because how do you know an asteroid is double, not single? From Earth, we normally just see a single point of light, and we do not know if it is 1 asteroid or 2 asteroids, and in rarer cases, 3 asteroids. Well, if 1 asteroid moves in front of the other, it will cause the light to change, to fluctuate, and it will do it in a regular way, and that tells us not only are there 2 asteroids there, but it allows us to measure exactly how often 1 asteroid, say the Moon, goes around the parent asteroid. If we manage to hit the Moon in that system and change its orbit, the period will change. And so we can measure the change in motion of a small asteroid Moon from Earth without needing another spacecraft there to measure just that one thing. And so that was the reason that a binary asteroid was chosen. And why Didymos and its moon Dimorphos? Because it was already known from 2003 that this was a large asteroid being orbited by a small asteroid, and we knew it would be back close to Earth in the year 2022. which meant that we would be able to make these measurements very accurately from Earth. And so that's why that system was chosen for the DART and Hera missions.
And this is also because at the time where we had the idea, so we revisited with our American colleagues in 2011 the idea of making something together because ESA could not implement the full mission by itself. We saw that maybe it's good to try it on an object for which we can measure something from the ground in case only the projectile goes end of the spacecraft. Unfortunately, we anticipated what happened because we launched in delay the second spacecraft, so it was good we could measure from the Earth. Another reason also is because since we don't really know what we do when we do a test, we don't want to move an asteroid around the sun to cause the risk we try to avoid. That would be a little stupid.
Yeah, it would be bad.
So, okay, so that's really, really great. And this little moon is only 150 meters in size, and you can imagine the challenge of doing so. So now we have done it. DART made the impact. We even have dust flying away at thousands of kilometers, and the Hubble telescope showed superb images of something that looked like a comet. There is so much dust, but now we need to go to the crime scene, you know, like the Colombo detective. We know the criminal initially, and then he does all the investigation. It's exactly the same. So we have the Colombo called Hera, and Hera is a cool mission because, as you have seen, it has a mother spacecraft and 2 CubeSats, interplanetary cubes. That's the first time we do that. And yet, it's still a small mission for ESA. So, Franco, tell us about what for you, because ESA already made extraordinary missions. You heard about Rosetta, landed a lander on a comet. Comet has a lot of gas release, dust, yet it succeeded. Even more impressive for me, the Huygens mission that landed on Titan. Titan is a satellite of Saturn. And that was Europe, 2005. We didn't talk much about it, big challenge. So it seems really challenging. You go to Titan, etc. But Hera has its own challenges. So what are the challenges for you? What were the difficulties you had to develop Hera and the CubeSats?
Yeah, so thank you. One of the main challenges that we are confronting with Hera is actually the development time. Actually, we signed a contract for the development phase almost 4 years ago. And now we are about 1.5 months to ship the spacecraft to the Launch Complex 49 in the Cape. We are in a very exciting moment. For the last 10 months, we've been focused on basically performing the environmental test campaign. The environmental test campaign is that part of the testing that subjects the spacecraft to the conditions that we will see with the launch, but also during operations. So basically, what we did, we went through many, many challenges, and these testing campaigns are always very challenging. The first step was to put the spacecraft into a shaker to simulate the acceleration and the mechanical loads that we will see during the ascent phase on the spacecraft, and also when we separate from the rocket. After that, we tested the spacecraft in thermal vacuum cycling. So we put the spacecraft inside a chamber, which we put the vacuum, so we remove all the air, and then we thermally cycle it. So we put the spacecraft into very hot and cold conditions to simulate what we're going to see at the asteroid and during the cruise. So after that, we had to remove the spacecraft from the chamber and actually verify or perform the testing of the video that you saw before of the CubeSats separating from the spacecraft. Every time I see this kind of videos, they are very nice, but I see only requirements and I see only testing campaigns being closed, right? So from an engineering perspective, they are very nice, but they are very challenging. So after that, there was the first time that both CubeSats, Juventas and Milani, were together with Hera. And in order to get there, it was an extremely challenging, that probably Margarita then will talk about, because here we are pushing a little the boundaries of the CubeSat technology, the development time as well, but what we can do. So right after that, we perform what we call the EMC campaign, which is putting the spacecraft inside a chamber in which we simulate the void of a space. So we are able to communicate with the CubeSats and with ground over the air, basically. So we don't have reflections on the walls. And we are able to test that the spacecraft is able to coexist itself with all the subsystems, but also communicating with the CubeSats. And we did an amazing campaign there because we involve our colleagues from ESOC, which is the European Space Operations Center in Darmstadt, in Germany. And they were able to command the CubeSats from ground through Hera over the air. So that was kind of closing the link in between CubeSat, Hera, and ground all over the air. So these type of campaigns are extremely challenging, But we are getting there. We are 1 month away from shipping the spacecraft, or 1 month and a half, and very exciting to go to the Cape, finalize the last preparations, and see the rocket erected in the pad.
That's amazing. Look, I cannot believe it. And really, I must say thank you because, you know, ESA, the science program, makes missions which the time scale is very long compared to what happened here, and we can test science team that the schedule was crazy for the engineers. And I think one of the reasons why it worked, and I have another experience with another department of ESA, is because we have an integrated team. We are all working together. Engineers, scientists talk together, so there is an exchange. We follow what you do, you follow what we do, and therefore we move on together in a cohesion way, and that makes it much more efficient, and it's much more pleasant, of course. But it's really an amazing work to be ready. 4 years in space business is like tomorrow, and they really did a great job, and cannot imagine we launched on the 7th of October. This is absolutely crazy. So with a mother spacecraft, 2 CubeSats, we heard about Juventas, and I want to talk about Milani, which, by the way, the name of Milani, can you tell us why? Margherita.
Sure, yes. So, first of all, I want to say that whoever is familiar with football in Italy, Milan and Juventus are two football teams. I want to reassure you that this has not had anything to do with that. So Juventus project started before us, like a couple of years before, and so they already decided their name. We came after, and let's say the proposal came from ESA to give the name to a mission in honor of a scientist, Andrea Milani, who was the first one having the idea of this concept of having a combined mission. Then someone will correct me, but the combined mission of an impactor and a chaser after. So he was the first one elaborating this concept, and he passed away a few years ago. We didn't have the chance to meet him, at least I didn't. And so, of course, we accepted the proposal to, you know, dedicate our mission to him. So there is this couple of names, but the reasons is not the football, Italian football.
I didn't realize that, but I mean, France is rugby, Italy is really football, huh?
Yeah. So in Italy, in the conferences of Italy, is the first question I got, after my speech, that's the first question I got. So I wanted to just put this on the stone now. So
Andrea Milani was actually one of the proposals of the team of Don Quixote that we recommended.
And actually, another nice detail is that we recently had our logo identified and selected, and we had the delivery event of Milani to ESA in our office in Torino, and we had the honor of having the daughter of Andrea Milani, Alice Milani. She's like a graphic designer, and she helped us in selecting the logo, and she was hosted in our office just to announce to the public the final mission logo. So this was, you know, closing kind of the loop of having someone of the family celebrating this part with us.
Absolutely, and Andrea was also an artist, a writer, and somebody screaming in his office also. It was really the Italian atmosphere when you were working with him. It was excellent. So what was for you the challenge to develop Milani? Because Milani, so tell us what he's going to do in terms of science, and what were the difficulties?
Okay, for the challenge is how much time I have to answer that, because I have to select that. So, as the colleague of GomSpace told, our mission goals are complementary to the other one, and so we are more focusing on the external surface of the asteroid. And so we have 2 main instruments. One is the aspect payload. This is an hyperspectral imager aiming again at imaging the asteroid. So we are going to orbit around the asteroid and doing hyperspectral imager with this payload in 4 spectral channels.
So this is to measure the mineralogy of the surface.
Exactly. So that's what I learned from the scientists when I started to work on this mission. And then we have another very small instrument which was developed in Italy. This is a dust detector. So it's a sensor put on the external surface of the CubeSat. And the objective is to hope that some particles that are orbiting around the environment of the asteroid will just pose on the sensor, and so that we can measure some properties. Alan, please correct me if I'm wrong, but based on these measurements, we can get more more insight and more information of the internal composition of the asteroid. And so this is a very small, is impressive what it can do, but yeah, it's a secondary instrument of the mission, again, focusing on the external environment of the asteroid. Then we have another instrument, which is like in the middle, technology for the avionics of the spacecraft and a payload. This is a navigation camera. Let's remember that we are in deep space. We cannot rely on GPS signals and the navigation around this object, considering that there is the asteroid, there is Hera, and the other CubeSat. So the navigation around this object is pretty complex, and so we, of course, we have to rely on our navigation camera. But we have learned during the study and during the project that this can also be used as a scientific instrument. And so we can expect also images from this additional payload, again, bringing more data and more images to the scientific community. So that's more on the science. And talking about the challenges, so the first one was this one. So I've learned that we are engineers. So my company is based on, space engineers, electronics, software, whatever, but engineering part. And talking with a scientist, all respect, but can be, can be challenging because they are two different worlds. So they have to explain us what they want to do. We have to explain them what is feasible to do. And the two things are two extremes, and we have to work together to find, a middle ground, a common way that is making everybody happy. And so this was, for sure, at least for me, for our team, part of the challenges. The timeline was crazy. Franco was telling that we started this program in September 2020, which is a year that we will remember forever for other things, and we worked on the proposal phase during the COVID moment. So let's say it was a very tough preparation. Already from the proposal stage, we understood this was having a challenges. And for the first 2 years, we did all meetings remotely. So we didn't really meet with anybody. My first face-to-face meeting was the workshop in Nice, which was 2022.
On the beach.
And it was the first time that we gave, faces to mail addresses, not name, mail addresses. So this, for us at least, we are very new to the community of the planetary defense. It was our first mission. And so having, let's say, half of a project remotely, for sure, has had an impact. And then I would say that the number of interfaces that we had to cope with. So we are physically integrated into another spacecraft. And so mechanical interfaces, electrical, software, safety, EMI, EMC, let's say there were many requirements on the interface part that we had to cope with. And also every part of the interface was developed by a different entity. So the deployer was developed by ISIS, the life support interface board from another company. So also in terms of, putting a lot of companies together to then understand what was the best solution for a specific requirement was really a challenge. And I have to say that in here, the role of Franco, who was kind of the collector, having the big picture of everything, was extremely helpful because, of course, otherwise, let's say, it could have been really spread around the whole team, and he helped us a lot in talking to the right people, talking to the specific competence to have, the final solution defined. And all this, I think, was possible also because we had a fixed date of launch to respect. And so in big projects, you tend to, want to do everything perfectly, and so you delay decisions, you want to really fine-tune and perfectionize the different things, but here we couldn't have really this luxury, let's say, and so we had all together, scientists, engineers, ESA, to have a pragmatic approach and take decisions really fast because we couldn't really miss the launch date.
So next time I should give you a shorter deadline, which actually may happen. Because if we go to visit Apophis, we will talk about it probably just after. But before that, I want to say, and that's the scientist speaking on behalf of all the team, that we have, we have a strong recognition, we say in English, or we are really grateful for what you're doing, because the challenge for the engineers, you have to realize that our knowledge, scientists, when we go to see a new asteroid, relies on the light that they reflect and that we see from the Earth. So basically, the knowledge is, I would say, almost useless for the operation people and the engineers who ask us, Patrick, will there be sand like in Saint-Tropez, or rocks like in Nice, or will it be bare rock? And we don't know. That's why we go. But they need to have this information because, like, if you want to collect a sample, you need to know what kind of tool you're gonna use. And in fact, so far we have always been wrong. We went to a body, we told, that was NASA, OSIRIS-REx mission, we said, don't worry, you have an accuracy to land of 50 meters, no problem, there will be sand everywhere, smooth. Then we arrive full of rocks. And in that case, it's interesting in the operational room because on the left, you have the scientists, they are always happy. When they are wrong, they are happy because there is a new challenge. And when they are right, they are happy because they predicted something. So we are jumping like hell, and then you have the engineers looking at, okay, now what do you do? And the crucial thing, which is absolutely amazing, is that they find solutions to adapt. And that's the same with the operation engineer at Visa. We tell them, you ask us questions, take our answers with caution. I say, yeah, okay, we're right. And they are, they can adapt. While it's very incredible, like a thing, and I'm going to ask you that. The thing is, we don't know yet whether there are still some boulders around Didymos that were, remnants of the impact. We know the dust is away because dust is small, there are escapes due to the solar wind. But the big ones, like 1 meter or something, decimeter size, we cannot see them from the ground. We don't know. So we gave statistics. We expect maybe there will be a few tens, but of course the speed is very low. So we are okay. But, they have to deal with these uncertainties. So Alan, what do you think? Okay, if I say will be the biggest surprise, but then it's not a surprise if you already expect it. But what don't you expect?
What do I expect? Well, I expect we will be surprised. No, the amazing thing about asteroid missions and missions throughout the solar system is that we try to use our scientific knowledge to predict what we will see when we get there. And every time we go there, we see something we did not expect. And that is the beauty of this, because this is primarily a mission to help us defend our planet from asteroid impacts. But at the same time, we will find out new scientific facts about asteroids. And for example, Dimorphos, our primary target, will be the smallest asteroid we have ever studied in any great detail. It may happen to be the most likely size of asteroid to cause us problems, if you know what I mean by problems, in the future, or in the next 100, 200 years or so. But also, as Patrick was saying, it may be, for example, it may not be, it probably isn't the same shape now as before DART hit it. What will that shape be? There have been some fantastic studies done by Sabine Radigan and her team, but we don't really know what we're going to see until we get there. And so that's going to cause extra problems, I'm afraid, for the CubeSats and Hera itself. But we will have 3 eyes there of various forms in that asteroid system for at least half a year, hopefully a year. And we are going to find out so much new stuff about asteroids and what we can do to protect ourselves from them I just can't wait for the end of 2026.
Yeah, and in
fact, not long to go.
Yeah, and in fact, thanks to ESA and Hera, we will fully document this impact experiment so that we can extrapolate this knowledge to other scenarios. We will validate the numerical models. So it's absolutely amazing. And the good thing is that although we are still in the learning stage, what they are, how do they react when we interact with them, by doing all these missions, we learn so much each time that I'm hopeful that, within a decade or 2, we'll be better prepared to know what to expect and how they react. And this is because you have this fantastic mission, the Emirates mission to Asteroid Belt. They will big flyby of 7 objects. So then you start to learn more and more. You will see the diversity, a lot of things, and they will land on another one, so we'll see how it behaves. So this is a kind of mission that really allows us to improve not only the understanding of the solar system, but also how to cope with them in order to deflect them or to make resources. But in 2029, we have this Apophis asteroid coming to Earth. So, you know, I always tell my students, when you talk about planetary defense, think about the reality. There is no immediate threat. I mean, we have enough problem on Earth. If we had another one, we don't have people happy. Huh? So we have enough, but we know in the long term it will happen, and this is an advantage. This risk, we can predict it and prevent it with reasonable means. So we implement them so that we can prepare for the next generations. Unfortunately, in the case of Apophis, although I try to say that when I say it happened the Friday the 13th, people don't believe it. But you shouldn't be superstitious because we are absolutely sure it will come at 32,000 kilometers from the Earth. We have an uncertainty of 1 kilometer or even less, so it's nothing. And you will see it with the naked eyes. And that's incredible. It happens only once several millenniums. So it's a unique opportunity.
I'll also point out it's visible just by eye from Europe.
Yeah, from Europe. For us, Luxembourg, Nice, of course. Rome, Torino. No, just for us, Europe and Africa. And 2 billion people, depending on the birth rate, at minimum, will see this. And at ESA, working on a mission called Ramses, whose aim would be to go to visit it, to measure how the tidal forces of the Earth could change the properties. So far, all the interactions were done by humans, sampling, deflecting. Here, nature does the job for us, and sending images in live to the public that will see the light, and everybody has now a screen. On the screen, the real asteroid. That will remain in the collective memory, which is absolutely fantastic, knowing that the OSIRIS-REx mission by NASA is going to see Apophis, but will arrive 1 month after the closest approach. So it will give us superb data from the aftermath, but we have to have a mission to compare the before and after. So this Ramses mission is under study at ESA. Can you tell us a few words about it and the time scale and what the strategy? And then I think we'll have to.
Yeah, so since we didn't have enough work with Hera, part of the Hera team, we've been involved on designing the Ramses mission. So Ramses mission makes sense from the point of view of reutilizing the technology that we have developed for Hera. So same spacecraft or very similar spacecraft platform, a few different instruments coming from international collaboration and requirements and requests from scientists. We have to modify a few things because Apophis is coming extremely fast, flying by the Earth. So the braking maneuver that we need to perform, it has a very large delta V. Therefore, we need to extend or protrude the tank, so have more propellant on board Hera. So there are a few modifications that we need to do. But yeah, we are studying. We are already at the phase of approximately preliminary design review. In a couple of weeks, there will be, because this mission is not only science and engineer, there is also a lot of programmatics and financial decisions. So in a couple of weeks, we will know a little bit better the decisions. But it's an incredible, interesting, also international collaboration mission because we are in discussions with JAXA, we are in discussions with NASA, we are in discussion with a lot of international players to actually contribute to the mission from an engineering, but also from a scientific perspective. So the idea will be to launch Ramses in around April 2028. So very short development, even more challenging than Hera. But that's why I say that it makes sense. Well, I don't know if I should say this because I'm shooting myself on the feet, but it makes sense from a technological perspective because we can reutilize a lot of the technology, and we can actually even use some of the fly spurs that we built for Hera. So it takes a lot of work. It's going to be very challenging, but from a scientific and technology perspective, it's going to show what we can achieve in a very short time. We can respond. We can be there very quickly. And the idea is to rendezvous with Apophis approximately 1 month before the close encounter, and then almost live streaming, but take images as it passed through the Earth, and then also take the images after the close encounter, so we can actually compare the pre and post encounter, because probably the scientists can explain better what we can see with the tidal forces and how the influence of the Earth gravity can affect the surface of the asteroid.
Yeah, and so to end with this and with this fantastic panel, there are two key things with Apophis. So with space mission in general, that for the young generation, the concept of long-term efforts, because we always want instantaneous likes. So long-term effort, perseverance, and continuity. Like, took 20 years to build this expertise, and Apophis offers the opportunity to keep it and to maintain it and to exploit it again to another object, and this is absolutely fantastic. And the second advantage is that when you have 2 billion people watching, it's a better advertisement than the Super Bowl for the agencies that are involved. So even just for that, you can pay because the return will be amazing. So thank you so much. It's a golden age of asteroid exploration. I have actually a slide where you see all the missions that are going on. We have until the mid-2030 at minimum, a lot of new images of new asteroid, new discoveries. You saw one with the Emirates mission to the asteroid belt. There is also the Lucy mission by NASA, the Psyche mission, the Hera, the Ramses, the Hayabusa 2 Sharp, the Osiris Apex, blah, 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 blah. Thank you very much. Thank you, wonderful panel, and have a good evening.
Thank you so much, Patrick, for an extremely entertaining presentation here. Before we go, where is Maud? She's probably down in the museum. I'd like to thank you all for being in here with us. I'd like to thank all our people who are watching us online for being there. I'd like to thank the staff at Cercle Cité for helping us with the presentations. Thank you very much indeed for that. And I'd like to thank all our sponsors for tonight, and hopefully we will see you down in the Museum of Natural History now for another 2 or 3 hours of pleasantries. So hopefully we'll see you down there if you know how to make your way down there. If not, please ask any of us and we'll guide you, or we can walk together. It's actually not far away from here to walk. We just have to catch the elevator down to the other part of the city. And from there, it's like 5 minutes walk.
And thanks to the Asteroid Foundation, because thanks to you, every year, you give great visibility to this science, planetary defense, and for us, it's a superb opportunity to show to the world what we're doing. So thanks for all the organizers and for the foundation for doing so. It's very important.
Thank you so much indeed. And my colleagues from the foundation, there are 3 here tonight. Boje is up there. Can you stand up, please? He's a new member there. And there's Razvan there. And our chairman, Marcus, is sitting here as well. And thank you so much. And hopefully we'll see you down there in like 15, 20 minutes. See you soon. Thank you.